We now turn our attention to some particular classical solutions of the Navier-Stokes equations, which will lead up to them. This brings us to a historical figure. Augustin Louis Cauchy is French through 1857. He's an engineer and physicist and mathematician, and he was educated in civil engineering, much like Navier. His contributions include mathematical analysis and continuum mechanics, which is well known today. He is a prolific writer with over 800 articles and 5 textbooks, and they were mostly single author. These concepts and theorems are named after him, and perhaps more than anyone else in history. And the mathematician Lagrange was also a friend of his family. If you go to the Eiffel Tower today, he'll have one of 72 names inscribed on it, including that of Navier. He was a royalist and a Catholic, which is certainly beneficial in his career. Let's examine the particular classical solutions of the so-called Cauchy initial value problem for the Navier-Stokes equations. We'll seek solutions of the Navier-Stokes equations with reduced static pressure, P, and reduced density, and reduced viscosity, nu. Given a divergence-free field vector, u naught 0, the naught means initial, in 3 dimensions, R3, and a force in any time from 0 to infinity in 3 dimensions, we'll find some positive capital T and regular functions u and p in all time and space, subject to the solutions of the Navier-Stokes equations in incompressible form which we previously developed in equations 247 and 248, with the initial field being defined that u at time 0 is a velocity field which we'll call just u t naught notation. Here's the D'Alembert condition, divergence 3, and of course the momentum equation. We'll define a heat kernel W subscript T, which we'll use to solve the heat equation first, one of the most 3 fundamental partial differential equations. Wt will go as the fraction 1 over t to the 3/2, with x to the t negative half, which we'll just write this way for the 3-dimensional problem. 1 over 4t to the 3/2 e to the negative s squared over 4t. T is time and x is particular position from any particular position in the flow field governed by heat conduction or the heat equation. We'll introduce a theorem. Let u naught be infinite space unbounded and be continuous, because of course we're incompressible, function in 3 dimensions. Then u, the solution to the heat equation, can be written as an integral, a convolution integral with the heat kernel, with the initial velocity and time. This is a small typo here, excuse me. It's the difference between x and y with t, comma t. It'll be continuous in time and space, continuous, infinitely differentiable in time and space. And the solution of the equation can be written 251. Here's the heat equation, and this is the initial condition, unbounded. We'll consider the solutions of the non-homogeneous heat equation, and we'll have a forcing term F. Let's introduce another theorem for that forcing function. We'll let F be a continuous function in all time and 3 dimensions, and continuous differentiable in the first variable in time and space. It'll be uniformly bounded and uniformly with special derivatives. So we can write equation 252, integral of time and space, ds, dy. There's your heat kernel, and here's this function f, convolution. The resulting function capital F will be continuous in time and space and differentiable. And the solution can be written as the heat equation. Partial f, partial t is nabla f plus f in time and space, given some initial definition in time and space. If the velocity field in the initial time with unbounded derivatives, the solutions u and f in the heat equation are unique in the class of functions that are continuous, where properties for all positive times t from initial condition t, as long as 254 holds. That's a premium for all times in 3 dimensions for derivatives that exist that are less than 2, as long as this is a finite value. Note that through this particular linear equation, we can assume that u naught is 0 is f of 0 and prove that u and f are also 0, simply by putting them in the equations. We can also consider a heat equation with positive viscosity. Then we only must slightly modify our solutions of u to obtain 255. Note that we now have a viscous term here, which is a positive scalar. Setting it to 0 will recover the original heat equation. So this is like a coefficient of heat conduction in the traditional sense, but we're setting it to viscosity. Same initial conditions, unbounded infinite time from time 0. Then we can write an equation, 256 from 255 in this way. It's the same convolution integral of the heat equation. Here's the heat kernel. The Poisson equation in Theorem 4, the classical solution. Let u naught be a continuous function in 3 dimensions such that this supremum holds and is finite. Then for some beta, the power beta, which could be 2 or 3 for instance, then the function u should exist and be the particular solution, the integral of the initial condition times some kind of Green's function. And then the solution can be written as 259. This is classic partial differential equations. Here, the Green's function will be different than the heat equation. It'll be 1 over 4 pi times the magnitude of x, the distance from any 2 points in the flow field. We'll show that this is indeed a solution. Let the Green's function be written this way, xj over negative 4 pi x cubed for 1 to 3. And then we can have partial uj is u naught convolved with gj, and partial ju is partial I u naught convolve Green's function. Then we can write 261, a limit of the sum of partial u partial with the Green's function. Using Green's or Odrogorodi's divergence theorem, and knowing that del g is 0, Laplacian of g is 0 on 3 dimensions, and that the sum of, say, sigma j partial jg is negative 1 over 4 pi r squared, which you might see is very much like a Green's function, we'll find 262. The nabla u is the integral of u naught minus u naught x minus r sigma d sigma, integrating it away in space. We'll find, after reducing 262, we'll find nabla u is negative u naught x. We can now turn to a history slide of George Green, who's British, 1793 to 1841, and he grew up at a windmill and didn't have any formal education when he made his major theories. He wrote and self-published an essay on the application of the mathematical analysis to the theories of electricity and magnetism in 1828. In 1932, he received a formal education finally at Granville and Caius College. He was elected a Fellow of the Cambridge Philosophical Society and published 6 publications on hydrodynamics, sound, and optics. Maxwell picked up his work to develop, of course, electrodynamics, quantum mechanics, and superconductivity. It was one Lord Kelvin who popularized his theory after he passed away.